So, hello and welcome to lesson 15. So, in lesson 15, we will talk about when the objective of our transportation model is to maximize it, right? So, we'll talk about a maximization transportation problem. So, I'm Boydo Randolph, a final year student of Mathematics KNUST, and I'll be taking you through this lesson. Please don't forget to like the video if it helps you and subscribe to the channel for more videos. So, what we have been doing so far is to look at the minimization transportation problems. So, now the question is, how do we go about solving the transportation problem when our objective is to maximize, right? So, there are certain types of transportation problems where the objective function is to be maximized instead of being minimized. These problems can be solved by converting the maximization problem into a minimization problem. So when you have a maximization problem, you first have to convert it to a minimization problem before solving it. But the question is, how do you do that? And that's what we are coming to learn here. So as we learn that with this example, it says a company has three factories located in three cities, X, Y, Z. These factories supply consignments to four dealers, A, B, C, D. The dealers are spread all over the country. And the production capacity of these factories is 310, 100, and 290 units per month, respectively. The net return per unit product is given in the following table, right? So this is a table that we have here. And the question says, determine a suitable allocation to maximize the total return. So here we are going to maximize total return. In the previous one, I've been trying to minimize transportation cost, but here we have to maximize the total return, right? So let's look at how to solve it. So it says this is a maximization problem. Hence, first we have to convert this into a minimization problem before we can solve it. And the conversion of a maximization problem into a minimization one is done by subtracting the unit cost of the table from the highest unit cost. So if you want to convert this problem into a minimization one, we ask ourselves, what is the highest cost here? You can see it is 8. So when we are converting this maximization problem into a minimization problem, we will subtract each of the cells from 8. So here, for example, we have 8 minus 6, which will be 2. 8 minus 6, 2. 8 minus 6, 2. 8 minus 4, 4. For all of them, right? So you could see that doing that is going to give us, this is for the table, 8 is the highest cost. So we subtract all the unit costs from the 8. And then we get the revised minimization transportation table, which is given below. So as I said, so you could see 6 minus 2, 6 minus 2, 5 minus 2, 3. 6 minus 2, 4. 7 minus, sorry, so 8 minus 6, 2. 8 minus 6, 2. 8 minus 4, 4. 8 minus 2, 6. 8 minus 5, 3. 8 minus 6, 2. 8 minus 7, 1. 8 minus 8, 0. So that's going to give us this table here. And now this is a minimization one. We've been able to convert the maximization one into a minimization one. So we will solve this using the normal procedure that we know. Okay, so let's try to solve the problem now as a minimization one because we've been able to convert it into a minimization problem. So we first have to find the basic feasible solution. And we are going to use the least cost method or minimum cell cost method to do that. When we do that, we are going to get this here. So we'll do assignment to the ones with the least cost. So we started with this one, 290, and we have to make sure that all the column and row rim requirements are satisfied, right? So this is what we get here. So you see, when we get here and we are calculating the total return, we don't calculate them using 150 times 2, 130 times 2. That's the only difference. So we go back to the original table, and you could see these two here. The original table, it was what? 6. So we use these cost, right? These sales, right, to calculate the total return. So here to be 6 times 150. Here to the original one it was 6. So 6 times 130 plus 6 times 30. Then here in the original one it was 4. So 4 times 90 plus here in the original one it was 5. So 5 times 10. And here in the original one it was 8. So 8 times 290. And this will give us 4,590. So the next thing for us to do is to check and see if this table is optimal, right? By using either the stepping stone method or the modified distribution method, right? So we develop our modal equations and you know how to develop them, right? So you could see here, for instance, we have ux, then here to be plus va to be equal to these two here. When we come here to be ux plus vb equals 2. So we use that same concept to develop all of these. And when it comes to solving it, we always take the first one and we assume it is 0. So we let ux be 0. And when ux is 0, then you get these resulting values. Alright. Then after that, we calculate what we call the net cost changes for the empty cells. And that one is given by what you can see here. So when we come here, we take, for instance, this empty cell, right? So this empty cell will be called KXD. And for this empty cell, KSD, the net cost change will be CXD minus UX minus VD. So CXD is the 4 here. Then the UX and VD were computed from here. So we make that substitution and we get plus 3. So we do that for the rest of the empty cells. So the empty cell KYA will give us 0, KYB will give us plus 2, KZA will give us plus 2, and KZB gives us plus 1, and KZC gives us 0. So you can see that since none of the KIJs is non-negative, it means that optimal solution is stretched. So that means that the table we have here is our optimal solution, right? So thank you very much. Enough of the transportation models or problems. So in our next video we will learn how to solve assignment problems, right, using the Hungarian method. So thank you very much and see you in the next video.